Hey everyone, so I was watching a recent episode of the new series of Mythbusters. Overall, I'm really enjoying what they're doing. The new guys have great chemistry, it's a very fun show. But watching episode 2, I found myself a little disappointed that they didn't go as far into the math as I would have liked. I think the older Mythbusters would have gone a little deeper into the science of what they were doing, as opposed to just the actual myth. So I decided, sitting there watching the episode, that I was going to solve what they were doing mathematically using the science of stoichiometry. Now, if you haven't seen the episode, what they're doing is they are trying to discover whether or not they can launch an intruder, a burglar, out of the chimney using a leaky fireplace. The fireplace runs on propane, and the overall idea of the episode is that you need the right ratio of gas to air in order to get ideal combustion. Okay, so the idea behind stoichiometry is that the number of products must equal the number of reactants. In this case, our reaction is between propane, our fuel, and oxygen, our oxidizer. Now, propane has a chemical formula of C3H8, so we have 3 carbon atoms with 8 hydrogen atoms. Oxygen, in its standard form, comes in O2. This is the most stable form of oxygen you'll find in the air. So, in order to do stoichiometry, we must say that some combination of C3H8 and O2 must yield its likely reactants. So, looking at these, we know that during any combustion, one of our most likely combustants, or reactants, is going to be CO2, right? So I'm going to guess that one of my reactants is CO2. CO2, carbon dioxide. Now, looking at this, I can also see that we have a lot of hydrogen and a lot of oxygen. So likely out of this production, we're also going to get quite a bit of water. Now, water is obviously H2O. So we're going to get also some amount of H2O. Now, in order for this reaction to work, this equation must balance. The number of components we have over here on the left before the combustion must equal the number of components we have over here on the right after the combustion. Over here, looking at our right side of our equation, only one of my products has hydrogen in it. Now keep in mind, these are our likely reactants, they're not our actual definitive reactants. We could also get carbon monoxide, we could get nitrogen monoxide, we could get nitrogen dioxide. There's a lot of others we could get. So these are an educated guess of what we're going to get. So, looking at our right side here, we have H2O. That is my only product with hydrogen in it. Over here, I have 8 hydrogens in our propane atom. So, there's 2 over here, there's 8 over here. I have a minimum of 4 water molecules I'm going to get out of this reaction. Well, okay, looking at that, I've now used all of my methane from over here, and I have used 2 O2 molecules. But I also have CO2 over here. Well, if I look over here, I have 1 CO2 over here, I have carbon 3 over here. So I need to use all of these carbons. So I'm going to have a minimum of 3 carbon dioxide molecules. Well, okay, at this point, I now have 3 O2 molecules used to make those carbon dioxide molecules. Well, okay, 3 plus 2 is 5. We could assume that I have 5 O2 molecules and only 1 propane molecule. As it turns out, this equation is now balanced. So now that we have our equation balanced, we know that we need 1 propane molecule for every 5 oxygen molecules used. From there, we can go figure out what percentage, volume-wise, we need in order to actually have our correct stoichiometric ratio. Now, in the episode, they found that this was 5%, gave them the most dramatic reaction. Let's see if that's true. Okay, so now that we know the ratio we need for the molecules, we need to figure out how those correlate to volumes. For that, I'm going to go to the ideal gas law. So the standard form of the ideal gas law is pressure times volume is equal to number of molecules times the ideal gas constant times absolute temperature. Now, in this case, we're going to assume that both of our objects are at the same temperature. Our pressures will both be at atmospheric pressure, and also the ideal gas constant is constant for all gases. So at this point, we can say that our pressure is the same for both of our materials, our gas constant is the same, and our temperature is the same. So the easiest thing we can do is solve this equation so all of our constants are on one side of the equation. So looking at this equation, we know that our volume of our substance divided by the number of moles will equal the ideal gas constant times temperature divided by pressure. We know that everything on the right of this equation will be a constant for both of our substances. So what we can say is that we need to set the left half of this equation equal to each other for both substances. Well, okay. We have some relationship between volumes and we have some number of moles. Well, we have one equation, we currently have two unknowns. Because what we essentially found in our stoichiometric ratio is we found the relationship between how many moles of one substance we need with respect to the other substance. So what I'm going to do is I'm going to say we need a minimum of one propane molecule, right? So I'm going to say that our N for propane, our NC3H8, is equal to 1. We have 1 mole. And for our oxygen, O2, we know we need 5 times that many. So our NO2 we will set to a value of 5 moles. Simply 5 times the value we have for our propane molecule. Now the other thing we need some relationship between the volumes. I'm going to say that our imaginary cylinder has a volume of 1 liter. Because then what I can do is I can say that 1 liter, our total volume of our chamber, is equal to the volume we have of oxygen plus the volume we have of propane. Now that I know the ratio of how many moles of each substance I need, I know a relationship between the volumes of my container, and I know a relationship between the volume and the number of moles. So what I want to do is I actually want to solve this for one of the two volumes I want. Now, the one I solve for out of this equation will be the one that I don't end up getting out of my equation. So that's something to keep in mind. I really want to know what percentage of methane I need in order to make this combustion work. So I'm actually going to solve this for the volume of oxygen, volume O2. So with that in mind, I'm going to take this volume of O2 and I'm actually going to plug it back into my relationship I developed from the ideal gas law. So at this point, I have one equation, all of these have placeholder values, and I have one unknown. So solving for this unknown, I should be able to find the volume required of our propane in order to have a correct stoichiometric ratio. So, it's going to take a couple steps to do the math. The first thing I want to do is distribute this denominator to each of the terms, bringing both terms of the volume of propane to the same side. Now that we have this relationship, I can factor out the volume of propane. And so finally, solving this for the volume of propane. So let's plug in our values. Now that we know our number of moles, at least with respect to one another, we can say that our volume of propane is equal to 1 liter over the number of moles of O2 we said was 5 moles over the number 1 over the number of moles of propane, so 1 mole, plus 1 over the number of moles of oxygen, which is 5 moles. Moles cancel, leaving us an answer just in liters. Now, multiplying these values out, we can find that this leaves us a value of 0.1667 liters. Now, if you've bared with me this far, we're almost done. In order to find the percentage of propane required, we need to divide our volume of propane by our total chamber volume, leaving us with this is equal to 0.1667. Now it's just a ratio, it has no units, so we'll multiply that by 100 to get it in percent, and we can find that the percent of propane is equal to 16.67%. Now, as I said earlier on in the episode, they tested a variety of ratios, and they found that 5% was the best. They did factually test 15% propane. So why did they get 5% and I got 16.67%? Well, the answer's simple. I base mine only on the products that react. Nitrogen, which is usually in the form of N2, is fairly non-reactive with things. Our air is roughly 70% nitrogen and roughly 30% oxygen. So there's only 30% of our reactant O2 in the air. So in order to get this down to the amount I need for just air, I need to multiply this by the 30% that is in air. So if I multiply this by 0.3, which is functionally 30%, a value of 1 would be 100%. I can find percent of our propane with respect to air is equal to 5%, which is the exact value they experimentally found in the show. So, I hope you enjoyed this episode of Pop Culture Science. If you enjoyed this episode, please give me a thumbs up and leave me a comment for other things you would like me to go over. I'd be happy to try and fill in some information that's missing in normal TV. Thanks for watching and have a happy Thanksgiving. Till next time.